Properties of fibers. The properties of textile fibers can be classified into two categories: physical properties, chemical or biological properties. Physical properties are further classified as mechanical properties, moisture absorption characteristics, electrical properties, thermal characteristics, and optical characteristics. Let us now take up the physical properties one by one. First, mechanical properties. They include important parameters like breaking strength, breaking elongation, elastic recovery, and toughness. Stress strain. To study it, the fiber is held between two jaws in a tensile tester and is extended by moving one of the jaws at a controlled rate, and the load required to extend the sample is recorded on a chart paper along with its elongation as the sample elongates till it breaks. The load elongation curve so generated has to be converted to a stress strain curve so that the data is independent of sample dimensions. Since the cross sections of a number of fibers may not be circular, the most convenient way to do this is to divide the load by the fiber denier and quote the stress in gram force per denier, which is specific stress. The stress strain curve of the three major natural fibers are of man-made fibers are shown in figures. The end point of the curves indicate the breaking stress and the breaking strain among natural fibers. Wool shows considerable extension before breaking, while cotton extends much less. Wool has low breaking strength compared to silk and cotton. Among the man-made fibers, polyester and nylon 6/6 fibers have high breaking strength compared to acrylic and rayon fibers. Initial modulus. Initial modulus is estimated from the initial slope of the stress strain curve. Initial modulus or stiffness is the resistance offered by the fiber to the initial deformation and is defined as initial modulus, which is equal to stress strain at very low strain. A summary of mechanical parameters of different fibers is given. Natural and man-made fibers have a wide range of mechanical properties. Some interesting points are: acrylic fibers have mechanical properties close to those of wool and are in fact used as artificial wool. The initial modulus and breaking strength values of cotton and polyester fibers are quite close, so they can be blended. Amongst natural fibers, silk is closest to man-made fibers in its mechanical properties. For industrial uses, fibers with much superior mechanical properties are made by using high molecular weights and greater molecular orientation. Elasticity. Elasticity is a measure of the fabric's ability to return to its original form after being stretched or squeezed. The recovery of the fabric to its original form is time dependent and may be 100% at lower force. Nylon 66, wool and polyester fibers show good elastic recovery even while undergoing quite large extensions. Silk, viscose rayon and cotton show poor recovery. Resilience. This ability to recover after the fiber has undergone compression is known as resilience. Nylon 66 and wool possess high resilience. Durability. Many mechanical parameters may contribute to durability, and these include modulus, breaking strength, breaking elongation, abrasion resistance, etc. Man-made fibers are more durable than natural fibers. In the case of durability, nylon and polyester are on the top and linen and silk at the bottom. Moisture absorption. In hot and humid weather, one can feel very uncomfortable if the clothes do not absorb perspiration and moisture. If the cloth can absorb perspiration and moisture and maintain some sort of equilibrium with the outside atmosphere, this discomfiture is reduced. Natural fibers absorb moisture better than man-made fibers. An exception is viscose rayon. The amount of water in a specimen is generally expressed in terms of moisture regain, which is defined as percentage moisture regain is equal to mass of absorbed water specimen into 100 over mass of dry specimen. The moisture regain data for the major natural and man-made fibers is given. Third, electrical properties. Textile fibers are generally good insulators of electricity. Their electrical resistance is very high. When yarns are being processed or are being woven, or knitted into fabrics, the rubbing of fibers on the machine surfaces guarantees electrostatic charges which accumulate because the fiber does not conduct or dissipate the charge. Since water is superior conductor of electricity, the presence of moisture avoids accumulation of static charge. For this reason, in cotton mills, a high level of humidity is maintained. Since synthetic fibers have low moisture regain, the problem of static is quite severe with them, and flying sparks can sometimes be seen when handling polyester fibers. Fourth, thermal characteristics. Textile fibers are viscoelastic materials, which means that they combine the elastic behavior shown by conventional solids with the viscous characteristics shown by liquids. Thus, heat has considerable effect on fiber properties. On heating, the fabrics show significant softening. This confers dimensional stability to the product up to the temperature of heat setting. Fabrics made from natural fibers, on the other hand, do not show the typical softening behavior shown by synthetic fibers. Therefore, chemical processing is used to treat fabrics made from cotton, wool, and silk. Fifth, optical characteristics. When light falls on a fiber, it may be partly transmitted, absorbed, or reflected. The luster of fabric and the total visual appearance are related to the intensity of reflected light. Circular filaments arranged parallel to each other in the fabric will enhance the intensity because of speculation reflection and thus make the fabric lustrous. That is why mercerized cotton fabrics have more luster. Synthetic fibers are generally circular in cross-section and are like smooth circular cylinders. This gives them such high degree of luster that dulling agents like titanium dioxide are used to reduce luster.